Today we are going to talk about the second part, which is the pipeline in data path. So here we are going to talk about the control of the pipeline. In the previous class, we talked about this part, which is the data path itself. And now we are going to see how the control part is pipelined within the pipeline. How the control part of the data path is pipelined in a computer system. So as you can see here, okay, as you can see here, we have the instruction fetch. It starts with the program counter. So the program counter is part of the instruction fetch over here, which is the same part over here. Then we have the platform between instruction fetch and decode operand fetch. Now we have something called decode operand fetch. Previously we have instruction fetch, execute, write back. Now we have instruction fetch, decode operand fetch, execute, and then write back. So now we have 4 stages. Now as you can see, we have new platform registers which are used to hold the data between the cycles. Here all these are platform registers, and these platform registers are basically used to hold the data between intermediate stages. So as you can see, this become one stage, which is the decode operand fetch stage. So the instruction decoder and the register file are now in stage number 2. Click over here. The instruction decoder and the register file are in stage number 2. We have the function unit is part of stage number 3, and the register file now is in stage number 3. So these are the modifications that are done to the pipeline in the 4 stages, as you can see over here. Now, the main part that we want to talk about over here is how to use the pipeline. Now, if a pipeline should be able to handle 4 instructions at some stage, so all the 4 instructions will be there. Why? Because if we said here we have 4 stages, so we will have at least 4 instructions at the same time. So let's take an example for these instructions, which are instruction 1, 2, 3, 4, 5, 6, and 7. So you can see that we have instruction fetch, decode operand fetch, execute, write back. Instruction fetch, decode operand fetch, execute, write back. So instruction number 1, regardless of the instruction, we are not going to write the instruction because we are more concerned about how it is done. So this is instruction 1, instruction fetch, decode operand fetch, execute, write back. Then instruction 2, same. Instruction 3. Now the full utilization of the data path happens in cycle number 4 to cycle number 7. Here we are filling the pipeline, and here we are emptying the pipeline. So in clock period 1, okay, instruction 1 is instruction fetch. In clock number 2, instruction 1 is in decode operand fetch, instruction 2 is instruction fetch, and so on. Here we can see the utilization of the data path. So you can see that here, okay, you can see here in cycle number 4 we have full utilization. So we have 1. In cycle number 3 we have 3 over 4. In cycle number 2 we have 2 over 4, and cycle number 1 we have 1 over 4. So as you can see here, we have 2.5 instructions done in 4 nanoseconds. 2.5 instructions done in 4 nanoseconds. So to complete the program of 7 instructions, we need 10 clock cycles, which is required. The time required is 10 nanoseconds compared to 23 nanoseconds if we have done it in a normal instruction in a normal computer, where we remember that time it was the time was 2.4 nanosecond. Multiply it by 7, you are going to get the 23.8 nanoseconds, which is for a conventional data path. As for our data path, we needed 10 cycles, as you can see here, from cycle 1 to cycle 10 to finish 7 instructions, and each one of these is 1 nanosecond. So we multiply 10 by 1, it's 10 nanoseconds. So this makes our data path around 2.4 times faster than the normal data path. Anyway, we expected to have a 4-fold improvement, so we have 2.4. Again, it's not 4 times because of these 2 reasons. the delays are added by adding the platform registers. And remember, we are filling and emptying the pipeline. So in these cycles, we are wasting some time. In these cycles, we are wasting some time. Only from 4 to 7, these cycles, we are fully utilizing the data path. So in order to go further in pipelines, I want to explain the pipeline hazards. Okay, pipeline hazards. So first of all, let's have an example where we have this pipeline, which is a 5-stage pipeline. Here we have instruction fetch, instruction decode, execute, memory write back, and register write back. You can see this is just an example for a pipeline which has 5 stages, and we want to discuss the hazards that are available. So we have the structural hazard, we have the data hazard, and we have the control hazard. I want you to be able to discuss, to be able to identify these hazards, plus to see how we are going to solve their problems. So first of all, the structural hazards, structural and resource conflicts, where the hardware cannot support all possible combinations of the instructions simultaneously, where you are trying to write and read from the memory at the same time. Data hazards, you are trying to use an operand, but the operand is not ready yet. And control hazards, you are trying to jump, but your pipeline is already holding new instructions. So let's talk about structural hazards. As you can see here, instruction number 1, here we instruction fetch, we instruction decode, we execute, we memory write back. Now at the same instruction number 3, at the same time is trying to read from the memory. Here we are trying to write or even read, and here we are trying to read. So we cannot access the memory in the same cycle twice. Okay, we cannot access the memory in the same cycle twice. So this will give us a structural hazard. There's a problem in our structural hazard. The solution is basically to include a stall or a bubble inside the pipeline to delay this instruction for 1 cycle. So this will solve this problem over here. Okay, this will solve this problem over here. Again, this problem may or may not happen, depends on what is the natural of this instruction. So this instruction is load, means we want to read from the memory. Okay, now these instructions, you will tell me that here we have memory, yeah, but this instruction will not use the memory. Now the structural hazard will happen if we are going to use the memory. If we are not going to use the memory, it may not happen. The next instruction is the data hazard. Let me show you an example over here. The instruction is subtract S1 minus S3, put the result into S2. So my result will be in S2. The next instruction is to AND S2 with S5. Now if you look here, this is instruction fetch. The write back is going to be done over here in cycle number 5. Okay, the write back is going to be done here in cycle number 5. But for instruction 2 and instruction 3, we want to use the values of R2. But R2 is not ready. We still have the old value of R2, which is 10. The new value of R2, which is minus 20, we will be having in cycle number 5. Or even over here. The only one that will get the right result is this register over here. So here 10, half of the cycle it is 10, the second half it is 20. Here it's 20 and so on. So you can see that these registers here are taking the wrong information. And here, if our register file cannot support read and write at the same cycle, we are going to have the same problem. So this is called data hazard. To resolve data hazards, we insert NOPs. Okay, we insert NOPs, or we do forwarding. We forward the results. Okay. This is all forwarding the results, so you can see how it is done. The final type is the control hazard, and in the control hazard, like you can see here, it's a branch on 0, and at the same time, we kept including the new instructions, but these instructions shouldn't be there because we are going to branch. So this is also called the control hazard, and we need to know how to solve it. So we have 3 types of hazards: structural, data, and control. Structural hazard happens when you try to access memory at 2 times in the same cycle. Data hazard happens when you try to data hazard happens when you try to read information which is not ready in the register file. And finally, the control hazard is always there available when we have branch or jump. So hopefully this will explain. We will have more discussions on the online discussions. Thank you for